video, we're going to look at the first two tests that we have to determine convergence or divergence of infinite series, the nth term test and the geometric series. And we're going to start here with the nth term test for divergence. And this states that if the limit of a sequence, the terms of a sequence as n goes to infinity, does not equal 0, then the infinite series must diverge. Again, if the terms of a sequence as n goes to infinity, if those terms do not approach 0, then the infinite sum of those terms will have to diverge. Let's look at an example. If I've got the series 1/4 plus 3/7 plus 5/10 plus 7/13, and my general term here, 2n minus 1 over 3n plus 1. If I consider the limit of the terms of the sequence as n goes to infinity, that limit is equal to 2/3. And of course, 2/3 does not equal 0. And therefore, the series diverges by the nth term test. Let's look at another example. If I have 1 plus 1/2 plus 1/4 plus 1/8, 1 over 2 to the n is our general term here. In this case, if I consider the limit as n goes to infinity of my general term 1 over 2 to the n, this one does equal 0. And so in this case, when we may be tempted to say that this series converges, we cannot, because our nth term test can only be used to verify divergence. We can never write that a series converges by the nth term test. And so in this case, the nth term test is inconclusive. And we need to use another test. Now let's consider geometric series. A geometric series is a series that can be written in the form of a constant times a common ratio to the nth power. This r to the n, that is the important feature that we're looking for to identify a geometric series. And if I have an infinite geometric series in this form, if the absolute value of the common ratio is greater than or equal to 1, then we know that the series is going to diverge. If that common ratio is greater than or equal to 1, the terms are going to keep getting bigger and bigger. Or if it's greater than 1, the terms will keep getting bigger. If it's equal to 1, the terms will stay the same. And then as we sum up those terms in the series, the sum is going to continue to get larger and larger and larger. However, if the absolute value of the common ratio is less than 1, that means those terms are going to be getting smaller and the series is going to converge. And for geometric series, we can actually calculate what the series will converge to. This will not always be the case. We won't always be able to calculate this value, but for geometric series, we can. And it's going to converge to a over 1 minus r, where a is that constant term, the first term of the sequence, divided by 1 minus the common ratio. So let's look at the same example that we saw previously. We can rewrite this infinite series as 1 times 1 over 2 to the n. Not that you have to rewrite it like this, but I'm putting that in the form of a times r to the n. And so we can see that the absolute value of r here would be equal to 1/2, which is certainly less than 1. And therefore, the geometric series whoops, there we go, converges. And we're going to go ahead and calculate what it converges to. It's going to be the first term of that series, which we can see as 1 over 1 minus the common ratio. So 1 over 1 minus 1/2, which would be 1 divided by 1/2, which is 2. And so the sum of this infinite series is equal to 2. Let's consider another example. Let's say that we have this series. Infinite series of 5 to the n plus 1 over 3 to the n. And when I look at this, I see that that we have some constants raised to the n power. And if I want to identify that common ratio, sometimes it can be helpful to rewrite the term and get it into that form of the constant times the common ratio to the nth power. So I'm going to rewrite this. And I notice I have 5 to the n plus 1. I can think about that as 5 to the 1 times 5 to the n, because if I was multiplying, that whenever you're adding exponents, that means that you're multiplying like bases. And this is what I'm looking for here, is to get a constant or a base in the numerator and the denominator that's raised to the nth power, because when I have that to the n, then I can rewrite that part as 5/3 to the n. And then what I have left over is this 5 to the 1 out in front. And so now we have it in that form of a constant times a ratio to the nth power. And so in this case, the absolute value of r is equal to 5/3. And 5/3, of course, is greater than 1. Therefore, this geometric series diverges. Now I want to consider another example of one that may need some rewriting. Infinite series of pi to the negative 2n. And in this case, we've got our constant being raised to the n power, but it's also being multiplied by another power. And so what we can do here to rewrite is just to kind of split those up and think of this as pi to the negative 2 to the n, because if I'm multiplying exponents, that means power to a power. So I can just split them up here, and then I can see that the absolute value of r is that pi to the negative 2, which we might want to rewrite as 1 over pi squared. That, of course, would be less than 1, and therefore the geometric series converges. And because it's a geometric series, we can calculate what it converges to. My first term, if I plug in 0, that's just going to be 1 over 1 minus pi to the negative 2. And in this case, I think we're just going to leave it like that and not really any need to simplify. It's still going to be irrational if we do that. Okay, I want to look at one final example, but we're going to consider two different versions of this series. I have 3 times negative 2/3 to the n, and my absolute value of r, the common ratio here, is negative 2/3, which is going to cause the terms of the series to alternate signs, positive, negative, positive, negative. But when we're considering whether or not the series is going to converge or diverge, we always want to take the absolute value of our common ratio. And so my absolute value here would be positive 2/3, which is less than 1. Therefore, the geometric series converges to the first term of the series. If I'm starting at 0, then this becomes 1 times 3, which would be 3 over 1 minus negative 2/3, or 1 plus 2/3. So that would be 3 over 5/3, which is going to be equal to a sum of 9/5. What if we have the same series, but instead of starting at 0, we start the counting at 1? Same series, we're just beginning in a different place. So my common ratio, absolute value of my common ratio is still 2/3, which is less than 1. And in this case, the series converges to my first term here. If I'm starting in at 1, then this is going to be negative 2/3 times 3, which would be negative 2 over 1 minus negative 2/3, which is negative 2 over 5/3, which would be negative 6 over 5. And so the sum of this series, when we start at a different counting number, then our sum ends up to be negative 6 over 5.